Okay, another property that we have here which is very interesting and easy to prove is that for every function that we have in closed interval a and b that is monotone function, it could be decreasing, we will have that all these functions are integrables. Why? Okay, let's suppose that f is increasing. The decreasing is very similar, so you can do it by yourself. Is increasing in this A is one of the stream, B is another stream. All the values of the evaluation of the function in between, they will be also in between of these two, right? They will be greater than or equal to the evaluation of the function in A and less than or equal to the evaluation of the function in B for all the x in the interval. So f, in this case, basically f is bounded in this interval also. So let's give an epsilon, right? That x is a number k greater than 0, such that we will make this function less than epsilon, right? This is the distance, right, of the evaluation of the function multiplied by k, right? So let's take any partition that we have in between these intervals, such that the distance for all the subintervals inside of the partition, all the i's that we have, will be less than or equal to k. So we have to find this partition. We don't know which one it is, but we know that, let's assume that the x is 1. And then, since f is increasing, we can guarantee that the minimum value will be the stream left. I am talking left and right here because this is the real line numbers. So the left is the minimum values in this case, and the right one, the right part of the subintervals, will be the maximum one, right? Then for all i's that we have in between 1 and n, we will have that this difference of the upper sum of p minus the lower sum of p. What is that? We just write the same definition as it is. Basically, we have the summatory of the evaluation of the function multiplied by this one minus this another summatory, the evaluation of the function multiplied by the distance of the subinterval. But because this is a difference between summatories, we can put it together and we can have the factor out of the distance of the subintervals. However, we say it just here that we can substitute all these subintervals by a greater value k. So if we do this substitution, we move it outside because it's a constant value now, and this term will be greater than or equal to whatever we already have for the Darboux sums, right? But we said here that this, by the assumption, we said that this term will be less than epsilon, right? So what happened here? We have what we just said in the previous video. Let me show you here. I think I have it here. So whenever we have this function here for a bounded function in the interval, whenever it is less than or equal less than epsilon for a partition that we assume that A exists, then it is integrable by Riemann. Okay. Another property that we have here is that this is basically a different thing. If we have a function f be a continuous function between the interval, then f is integrable on a and b. So for every continuous function, we will have that is integrable if the interval is a closed interval. If f is a continuous function in a compact set, remember that the f is also uniformly continuous in that set. I think I will record another video for what is uniformly continuous, okay? But for now, let's assume that this is basically one of the good properties that we have from the compact sets, okay? So now, how can we prove this one? So given an epsilon greater than 0, there exists also a delta greater than 0 such that the difference of the evaluation of the function x and y in absolute value, right, it will be less than epsilon in between the distance of a b and a and b, okay? Whenever x and y is any number that we want in the subinterval in the compact set, and the distance between these two numbers is less than delta. So this is basically some of the definition that we have for the limits, if you remember the epsilon delta definition. So let's get a partition P, right, from x0 to xn. Be a partition of the closed interval in the real numbers, so it's a compact set such that the delta xi, which is the distance in between these numbers, right, is less than delta for all the possible subinterval that we have there, right, in I. Now f assume is maximum and minimum on each subinterval. So for each subinterval that we have here, we know that they will have a maximum and a minimum in there, right? Because it is continuous. So we know that there is a maximum and there is a minimum there. It's either the streams or is it in between. There exists a point xi and ti in this such that the evaluation of si will give me the minimum and the evaluation of ti will give me the maximum. And that is basically by definition. Then the difference in between, we know that this is also an assumption that the difference of the stream of the subinterval and the other stream of the other subinterval is less than delta. We can also say that the difference in between of the maximum and minimum is less than delta, because even if they are in the stream values, s of I and t of I are the stream values, they will be basically, in the worst case, they will be the same of this, which is already defined as a less than delta. So the absolute value of the difference of this is also less than delta, right? Then for every I that we have here, we will have that the difference between the maximum and the minimum, which is greater than or equal to 0, is equal to the evaluation of fti and the evaluation of fsi, right? Which we said that by the assumption is less than epsilon over the distance between a and b, right? Then we can just put this in terms of the upper sums and lower sum, and we will have this difference, right? And of course, this is the summatory of this m multiplied by the distance, and because we are talking about all the m's, if we have this multiplication everywhere, this is the distance basically for all this, so it will be this delta xi. So then what? We know that this is less than the summatory of all delta xi multiplied by the epsilon, right? But this part, all this summatory is basically exactly the same as B minus A, because all the partition will start from A and finish at B. So the difference in between will be the summatory of all the distance of the partition, and that is by definition. So this one will go away with this, and basically the epsilon is the result. Therefore, by the same argument that I proved in my previous video, f is integrable of this one, right? This is the definition that we have. Other properties that I am not going to prove it here, but it is good to know that we can utilize that, is that whenever we have a f and g be integrables on the closed interval, and we have a k which is a constant in the real line, let's say k multiplied an f is integrable, and we will basically define it as k multiplied by the integral of f. Okay. Another one is the sums of the final sums of functions also is integrable, because we will have the integral of the two functions, but is equal to the integral of one of the functions plus the integral of the other function. And the last one that I will mention here is that if f is Riemann integrable from a to c and c to b, then we can write the integral as the sum, the integral from a to b as the sum of the integral from a to c plus the integral from c to b. Thanks.